Right, ladies and gentlemen, let's continue with Chapter 4, Transient Heat Conduction. And the textbook I'm using is the textbook of Cengel and Ghajar, the 5th edition. Transient Heat Conduction, Chapter 4. So what is transient heat conduction all about? It is about the fact that normally we've got a body, an arbitrary body. Okay, and that arbitrary body is going to be in a coordinate system X, Y, and Z. And in this body, there's a position X, Y, and Z, and heat transfer always, or normally, is about the fact that we must determine the temperature at a specific point in a body, or we must get the heat transfer rate. And the heat transfer rate might be out of the body, or it can go into the body. It will go out of the body if this temperature is higher than that of the environment, and obviously the other way around, if the temperature of the environment is larger than that of the body. So that is the heat transfer rate. And then also the heat flux. The heat transfer rate, the units is watts, okay, joules per second, and the heat flux is watts per square meters. So in 90% of all heat transfer problems in the textbook, those three things will be asked, one of them. Okay. Now, in heat transfer, okay, you've already done it, and just for revision, the three different modes of this heat transfer. This heat transfer rate, Q dot, what are the three modes of heat transfer? The first one is conduction heat transfer. Okay. The second one, convection heat transfer. And the third mode of heat transfer is radiation heat transfer. Conduction, convection, and radiation. Okay. Now you've already done it last year in the first chapter of this textbook. The conduction heat transfer is being described by Fourier's law, which gives the conduction, the heat transfer rate, the conduction heat transfer rate as minus Ka multiplied by the Tdx. Do you recognize that equation? Okay. However, it's one of those things, it is correct, but actually not really correct. Okay. Because that equation is only valid for a one-dimensional case, steady state, etc., etc. Lots of assumptions has been made to this equation. So this is the 1D equation. There are also a two-dimensional equation, a three-dimensional equation, and much more complicated than this one. But this is the very simple conduction heat transfer equation. The one of convection says that the convection heat transfer is equal to the heat transfer coefficient multiplied by the surface area multiplied by the wall temperature minus the temperature of the environment. And that is Newton's cooling law. And the third mode of heat transfer is radiation heat transfer, and that is equal to epsilon, which is the emissivity, multiplied by the Stefan-Boltzmann constant, multiplied by the surface area, multiplied by the surface temperature to the fourth, minus the temperature of the surroundings to the fourth. The temperatures should be in Kelvin. Okay. So those are the three different modes of heat transfer. Now, this you've already done in chapter 1.6 in Cengel. Okay, so please go back and just read it again. The convection equation you've already covered in chapter 1.7, and the radiation one in 1.8. Okay, but that was just as an introduction. It wasn't all the detail. So in this textbook, we are going to look at these equations now in more detail. So in chapters 1 to 3, and that you've already done, is the conduction part. In chapters 6 to 9 is the convection part, and in chapters 12 to 13 is the radiation part. Okay. Now, chapter 4 one we're going to do now is sort of here in between these two chapters, because it has to do with conduction, but there's also in it a little bit of convection. Now, what is the difference between this chapter and all the other chapters? Okay. Now, if you can just continue underneath this one, underneath that one, underneath that one, and underneath that one. Okay. So there will be 4 graphs. Okay, so this one is for conduction. This one is for chapter 4 that we're going to do now. This one is for convection, and that one is for radiation. Okay, so radiation, convection. Okay, this one is going to be on transient heat conduction, and that is conduction only. Okay. Now, if we look at a graph of temperature as function of time, for all of them. Okay. In all these chapters, if you've considered a body and you want to determine the heat transfer rate or the temperatures at a specific point, then the temperature as function of time was a constant. Okay. The same with the convection problems. The heat transfer rate was a constant or the temperatures were constant. And the same for the radiation heat transfer. Chapter 4 is different than that of the others, because now what we're going to have here is that the temperature is not a constant. It changes as a function of time. So, what is important in chapter 4 is that the temperature is a function of time. It's not a constant. What are practical applications? And now I want you to help me with this. I'm not going to mention all of them, but I think many of you can think of some practical applications. Okay. What applications can you think of in engineering and in your personal life where this is important, where the temperature changes as a function of time of a body? For you as students, or for many of you, the most important thing is your beer. Isn't it? Okay. Your beer, the temperature of your beer. Okay. So somebody maybe forgot it in the boot of the car, and it's a Saturday afternoon, and now the rugby starts or the soccer starts, and you want some cold beer. So the question is now, how can you get that beer, the temperature of that beer, to decrease? Do you agree? Okay. But at the same time, you're going to have a barbecue. On the barbecue, you're going to put a thick piece of steak. Okay. When will it be ready? Yes, all of you have different methods to determine when it is ready, but actually the food will be ready. It can be medium rare or whatever. Depends on the temperature in the center. So there are many things these days that you can use. You actually get something that you can stick in, and then there's a thing, and you tell pork or chicken or whatever, and then it will tell you, is it ready or not? What does it do? It just measures the temperature on the inside. Okay, or a roast beef. Okay, so you would like to know when will it be ready. Other examples is when you boil an egg. The same thing, the temperature changes as a function of time. When you do some steel treatments of plates, of shafts, of an engine, a big complicated engine in terms of geometry, it needs to be treated in different places. You can, for example, look at solidification or making coatings. Just during a solidification process, for example, if you use a plasma jet, the temperature needs to be increased of aluminium to something like 15,000 degrees Celsius. Okay. So it needs to be controlled, and you need to understand what is going on. What other examples can you think of where you think this is important to know about how temperature changes as a function of time? No, come on, ladies and gentlemen. What about a satellite re-entering the Earth? Okay, that satellite, the temperature would be about 1,250 degrees Celsius when that satellite will have to come back to Earth. So there, the temperature changes as function of time. Before it enters the atmosphere, the temperature would be minus 20 or minus 50. Very, very low temperature. Then it would increase to 1,250 degrees Celsius when it comes back. Or that would be the temperature on the outside of it. Steel ball bearings, okay. Those of you working in, or for those of you who have an interest in the heating, ventilation and air conditioning industry, what examples can you think of? Helen? Ice storage, okay, ice storage. This building, for example, okay, or many buildings, to be very energy efficient, you build ice around tubes during the night. You build it to about 50 or 75 millimeters, and then during the day, you would melt it and use it for the air conditioning of buildings. And specifically, you do that because the energy at night is very cheap in comparison with the energy consumption during the day. Okay. The refrigeration of foods, what they call the cold chain, you know, any product of a farmer up to when you buy it, you know, the whole control of the temperature. In some things, the changes in temperature has to be controlled. If it is too quick, then there is damage. Okay. If it is too slow, then it would spoil. Any more examples that anybody can think of? You're a quiet class. Okay, so those are the practical applications of this chapter. How does everything fit together? And I think this is one of the biggest problems that students have. If we now think of geometry, in terms of the practical applications that I've mentioned, the geometries can be from a flat piece of sheet to a beer, okay, to a car engine. So the geometries can be from very, very simple to very complex. Okay, and the approach that we follow of solving the problem can also vary from very simple to very complex. Okay. Now this chapter builds into different phases. And students find it very, very challenging, specifically the first part that we're going to do, which is called the lumped system approach. So paragraph 4.1 is the lumped system approach. And they find it very difficult if I ask them a problem in the test or exam on transient heat transfer to figure out, you know, which approach should they use. When can they use this one, which is more complicated, takes a lot of time, or when can they use this very simple one? So this is one of the biggest challenges that you're going to have. So this chapter builds up to paragraph 4.4, where we're going to do multi-dimensional systems, we are going to do semi-infinite systems, and then the other part is actually here, the CFD part, where you solve it numerically, which you're doing at the moment in another course. So this is typically how you can do it. So you can, with very complex geometries, you can use a lumped system approach, which is a very simple approach, to a very complicated approach. And all these are being presented in this chapter. How are you going to know which one to use? You'll only be able to do that if you really understand the fundamental theory. So if you just go look for the equations and just want to apply the equations, then you're going to make the mistake of using the wrong approach. So please take note of that and concentrate on that. So if we also look at the different types of solutions, if we look at this type of solution, I've said it is simple. Okay. How does it compare to that of the other? It has a very, very important difference. Okay. So this is 4.1, the lumped system approach, and this is the other. Okay. Now with the lumped system approach, let's suppose we consider a body. Okay. And this body is originally at a temperature of 70 degrees Celsius. And let's suppose the environment around it is also 70 degrees Celsius. If that is the case, then I hope you will agree with me that the temperature in the body would remain constant as function of time. Okay? However, at T equals 0, we change the environment temperature to 0 degrees Celsius. So what is going to happen with the heat transfer rate? The heat transfer rate is going to go from the inside to the outside. Do you agree? So the heat transfer rate is going to do something like that. Okay. So if we now look at the two different approaches of finding the temperature as a function of time of this body, and let's suppose there's a point 1, and there's a point 2, and there's a point 3. Okay. With a lumped system approach, all the results, all three lines, lines 1, 2, and 3, are going to lie on top of each other. Okay? With the other approaches, paragraphs 4.2 to 4.4, we are going to get a differentiation in the temperatures. Maybe that's a temperature 4.3, 2, and 1. Okay. So the difference between the lumped system approach is that it cannot distinguish between the temperature gradients inside a body, while with the other approaches it can. Okay, so that is one of the very important things of the lumped system approach. So let's start with this paragraph 4.1, which is called the lumped system approach. Right, let's consider a body, and this body has a mass M, a volume V. Take note that V with a strike through is volume. Okay, it has a certain density, it has a certain Cp, and then it has a certain surface area around it. Okay, and this body is at the temperature Ti. At T equals 0. So the temperature right through the body is constant, maybe 50 degrees Celsius, 100 degrees Celsius, or something like that. Then, at T equals 0, things changes. And on the outside, we have a temperature T infinite now, and we have a certain heat transfer coefficient. Okay, so what is going to happen with that body now? Again, there are two possibilities. Okay. The one possibility is where the body is being heated. The body would be heated if the environment temperature is larger than that of Ti. Do you agree? Okay, so let's suppose it is that one. The heat transfer rate is into the body. It can be the opposite also, where it will be cooled. And that would be when the environment temperature is now lower than that of the environment. So those are the two possibilities. So if it is being heated, then take note, this is Q, not Q dot. Okay, Q, not Q dot. It's a function of time. And this also is Q as a function of time. Okay. So the heat transfer rate, in the beginning, the rate would be very, very high. But as the temperature of the body increases, the delta T becomes less and less. So the heat transfer rate becomes lower and lower. So this gradient here, the gradient is the heat transfer rate. the rate at which the heat transfer flows into the body. Okay, and that is delta T. We can have the opposite, something like that, delta T. Okay, so this is if it is being cooled. Are you happy with that? You follow? Right, now just in terms of general, because sometimes it's a little bit confusing. Joules is how much heat is into a body. It is like money into a purse. Okay, you can go and count it. Or marbles in a box. Number you put in. The heat transfer rate is Q divided by delta T, which is joules per second, with units of watt. So the heat transfer rate is like the rate at which you're getting money into your purse. Okay, or the rate is going out. So if you go on shopping on a Saturday, on a Sunday, you do too much shopping, and then the rate of heat transfer or the rate of money transfer out of your purse is the important thing. And obviously how much is in it is the Q. Okay, right. So if we now say, let's look at the heat transfer rate into the body. The heat transfer rate into the body, then we've set it is equal to Q divided by delta T. Okay. What would the heat transfer rate be into the body? I would like to come back to convection heat transfer. Okay. So on the outside, we've got an atmosphere, a certain environmental temperature, the heat transfer coefficient has been given. So the heat transfer rate is being described by Newton's law. And that would be equal to the heat transfer rate multiplied by the surface area multiplied by T environment minus the temperature T of the body. And the temperature T is not a constant. It changes as a function of time. Do you agree? So in the beginning, yes, in the beginning, when the temperature is Ti, then the heat transfer rate would be T environment minus Ti. You agree? But then very quickly the temperature is going to change. Okay? All happy with that? All right. Then that would be equal to the Q, the heat into the body, and that would be from thermodynamics would be equal to mCp dt divided by delta T. Okay? Right. Let's look at the mass. The mass we can write as the density multiplied by the volume. Okay? We can write dt as d multiplied by the differentiation to t minus a constant. And many people think I'm jippoing here. Okay, so remember this is a constant. So if you do the differentiation of this, okay, then that is equal to that. Do you agree? So it's just a constant in it. And then thirdly, we're going to say, well, let's make delta T equal to dt. Okay. All in that equation there. Okay. So if we do that, then we can say the heat transfer coefficient multiplied by the surface area multiplied by T infinite minus the temperature T, which is a function of time, is equal to rho V Cp multiplied by D, temperature as a function of time minus T infinite divided by dt. You happy with that? Right, so what we're now going to do is let's get all the constants together and let's get all the temperatures on one side and the time. Okay. So let's bring all the constants to this side. Then we can say it is equal to the heat transfer coefficient multiplied by the surface area divided by rho V Cp multiplied by dt is equal to d, the temperature as a function of time minus T infinite divided by T infinite minus the temperature as a function of T. You happy with that? Ladies and gentlemen? Okay. Okay. Now with the next step there's going to be a minus sign in it. And then many students say, but where does this thing come from? Okay. Very easy. All we're going to do is we are going to change these two. Okay. And let's write it to the left. So we're going to say the temperature is a function of T minus T infinite divided by the temperature T minus T infinite is equal to minus the heat transfer coefficient multiplied by the surface area divided by rho, the volume, and Cp and dt. Okay. So what did I try to do? What I've tried to do is to, on this side, generate a term which is equivalent to dt or dt divided by t, and on this side a term t with a constant so that I can do the integration. Okay, so that was the purpose of this manipulation. So if we go and do the integration now, and we do it from Ti to temperature as a function of T, now let me write it a little bit larger. Temperature Ti, I'm going to explain it just now, Tt, d, temperature as function of T minus T infinite divided by the temperature as function of T minus T infinite is equal to minus the heat transfer coefficient multiplied by the surface divided by the density, the volume, and the Cp, and we do the integration from 0 to T. So, what does it mean? It means that when T is equal to 0, the temperature is Ti. The temperature at the temperature time T, we want to know what is the temperature as function of T. Okay? You all happy with that? Right, so if we do the integration, then we get the ln of the temperature T minus T infinite between Ti and the temperature Tt, and that is equal to minus the heat transfer coefficient multiplied by the surface rho V Cp multiplied by T from 0 to T. Okay, so if we do the substitution in this, okay, there's just one step that I'm going to skip. Very easy, just go and put it in, and then you can make it neat, and then you're going to end up with the ln of the temperature as function of time minus T infinite divided by Ti minus T infinite is equal to minus the heat transfer coefficient multiplied by the surface area divided by rho V Cp and multiplied by T. Okay. To get rid of the ln, we make use of T, of E. So then we can say that the temperature as function of time minus T infinite is equal to Ti minus T infinite is equal to E to the minus Bt. Okay. Where B is equal to that constant, and that is equal to the heat transfer coefficient multiplied by the surface area divided by rho V and Cp. Right, so that is the solution for a lumped system. This term is a non-dimensionalized term. This term, B multiplied by T, is also a non-dimensionalized term. Okay. And I will give attention to that also with a later lecture. But if we now go and look at the solution for temperature as a function of time, okay, from originally when it was at Ti to the temperature that it should reach, T infinite. Because remember, this body was originally at a temperature Ti, and now there's an environment with a temperature higher. So at the end, after a very long period, this temperature must be equal to that of the environment. Do you agree? Okay. So if we look at the solution of typically this, then the result would typically look something like that. And that would be for a value typically of B1. Okay, so that value there. If we increase the value of B, then the results would typically just look like that. So that is the solution for the lump system. It's a very, very simple solution. However, this thing that I've mentioned, B multiplied by T, which is dimensionless. Okay. We are going to discuss it later. And write it here, because it's very important to discuss later. And it's very important. And how important it is, I'm going to show to you with the next lecture, by first doing two examples. Example where you can use the lump system approach, and then an example where you actually cannot do it, but without you knowing which one you can use. Okay. And then I'm going to come back to the theory, and I'm going to show to you how you can use this and what it really means. Because this is the thing that is going to help you to assist with this challenge that I've mentioned here. The challenge that you're going to have in tests and class and in exams. I'm going to give you a problem and you're not going to use which approach to use. Okay, so that term is going to help you with that. Ladies and gentlemen, thank you very much.